Section 2 here is molar mass, and molar mass is the number of grams, the mass in grams that you could weigh on a scale that is equal to the atomic mass of the element, and it's going to then equal 1 mole. And so this is going to be the power of moles, is that moles is going to allow us to count individual atoms without actually having to count atoms, because they're so tiny we can't, and it's just impractical because there's so many of them. What it does is it allows us to weigh it instead, and then we know that that mass is equal to a number of pieces, and we can abbreviate that number of pieces with moles, and so then we can make sure that when we're going to do a chemical reaction, that even though the atoms are different sizes and have different masses, that we have a proper ratio, a proper number of each atom, each molecule that we need for the reaction. So this section is going to get into how we calculate molar mass, and then the next section is going to get into using molar mass in mole calculations, and we're going to build our way towards doing those mole calculations with chemical reactions. So first off, molar mass is the mass of 1 mole of an element, or it could be a molecule as well, as we'll see here in a bit, and it is the atomic mass in grams. So if I have 1 mole of carbon atoms, then 1 mole of carbon atoms is 12.01 grams of carbon atoms. And of course we know that this is also equal to Avogadro's number worth of atoms of carbon. And so now we have 3 things there that are equal, and we can actually relate them through a variety of equalities. They show you just this one here, but we can do the opposite. In fact, usually molar mass will be expressed as the opposite of that, 12.01 grams per mole, or if you'd prefer, grams per 1 mole of the substance. And we can use either one of these ratios for doing calculations. So here again are those 3 ratios, and the mass of elements on the periodic table have those individual masses. They also mention that they go out to 4 sig figs, which is why these here go out to the hundreds place, but these here only go out to the tens place. Personally, I prefer to use a mass that's bigger than any of my measurements. As I mentioned before, we don't want to let conversion factors limit us. We always want the measured values to be what limits us in a calculation. So as long as the mass that you're using from the periodic table is equal to or greater than your number of significant figures in a measurement, then you know that it's going to be your measurement that limits you and not the mass from the periodic table that limits you. So like I mentioned, every element and every molecule made up of elements has a different size and a different mass, and so then that means we have a different amount in terms of volume and mass of a chemical for it to be equal to 1 mole of that chemical. But all of these here, even though they have these drastically different sizes, are exactly 1 mole, which means we have an Avogadro's number worth of pieces of those. For sulfur, that'd be 32.0. I think it's 8. You'll want to double check that. Iron is 55.8, and these would be grams. Sodium chloride, something around 55.85. These last 2 here I'd have to calculate out. I don't know chromium, I'll be honest, and I'm not trying to show off here, but we're going to actually get into an example calculation over how to do this. And keep in mind, that is per 1 mole. And so all of these, they are molar masses that I'm writing out here. And I'll actually, after doing the next examples to show you how to do this, encourage you to come back here, check my work on this one, and try these 2 on your own. So this example here wants us to calculate the molar mass for lithium carbonate. And so what we're going to do, and the way that I like to do these, is we need the mass of lithium times the number of atoms of lithium. And we'll add that to the mass of carbon times the number of carbons, and we'll add that to the mass of oxygen times the number of oxygens. And so the way I like to show that is I jot down the mass first, and then I multiply it by the number. And frequently I'll lock these in with parentheses just so I can know that I have that. Now I know that 12.01 times 1 is going to give me 12.01. But I write that down so that I don't forget to make sure that I have multiplied by the subscript on all of these. It just helps me check and make sure that I've set up the problem correctly. And so there's our setup. Once we do that and we punch into a calculator, you'll find that it's 73.89 grams, and that's per mole. A couple things I'll point out here. First off, they said they go out to 4 sig figs. There's a few elements that are lightweight enough where they would have to add another digit to the decimal place here. I don't know if they actually did that on this one. I pulled that from my periodic table, which isn't the same one as what's in your textbook. But all of these go out to the hundredths place, which is why we would round this one out here to the hundredths place. We also don't let the numbers here limit us, the 2, the 1, and the 3, and that's because those are exact values. And so there is your molar mass of lithium carbonate. Now, your textbook goes through a much lengthier process to prove that this is actually a per mole, and yes, it is. You are certainly welcome to work it out that way. It might help with explaining why it is this way, but I think this method works just fine. Doing this one, I'm not going to do as much preamble and setup here. We start out with the carbon. It's got a mass of 12.01, and there's 2 of them. We add to that the mass of hydrogen. Hydrogen has a mass of 1.01, and there's 6 of them. And oxygen has a mass of 16, and there's 1 of them. And so punch that into a calculator, and you get 46.08 grams per mole for C2H6O. I encourage you to go back to the slide with the pictures and try those last 2 then, and to check my work on that other one, but that finishes up section 2 already.